Yeah, hello, and welcome to today's lecture on graph theory in transportation network. My name is Oluwaseyi Ajayi, and today we are going to be looking into the concept of graph theory. We are going to be looking at some applications, and before we do that, we are going to be looking into the transportation network and what it entails and the planning. So without wasting much time, let's get on into it. It says a transportation network in transportation planning refers to the infrastructural system, what allows the movement of people, goods or vehicles from one location to another is what we call a transportation network. What facilitates it for it to be possible? In one of the videos I made earlier, we talked about a transportation system, and we said in a transportation system, we have the infrastructure, we have the vehicles, we have the facilities, we have the operations and the users. And under the infrastructure, that is where we have the railway, we have the highway, airports, the ports, the public transit. So all this infrastructural system that allows the movement of people from one location to another is what we call a transportation network. So we're going to be looking at how this can be planned and how it is quite efficient through the use of graph theory. And in transportation planning, all this network needs to be analyzed to ensure that it is safe. The major and the number one important part of any transportation system is the safety. The safety of the movement of people and goods from one location to another must be assured. And that is the reason why we have all this form of planning the networking to make sure that all these things are well analyzed and optimized in order to ensure safety. And this involves the development and design of transportation routes. Whether there is an existing one, yes, there is going to be a development, and if there is going to be a need to design a new transportation route, that will also be taken into consideration, and the implementation of policies to manage traffic flow. So here we said that mathematically transportation network planning is more like a model which is represented in form of graph that we're going to be looking at in the later part of the lecture, and where nodes represent the locations and not just locations. We said node is just like a thing, a point or a location, such as cities and intersections, and we have what we call the edges. If we don't want to call it edges, it can also be called ties. It can also be called links. It can also be called relations. So all these things, the relationship between the nodes plus the links gives us a graph. And there are a lot of optimization techniques that have been developed through the use of algorithms like the J-Scales algorithm, like the Bell's algorithm. So this we're also going to be looking at in the later part of this lecture. The common goal of transportation network planning. Yeah, we have a goal. Why do we plan? Why do we have a transportation network planning in place? Why do we have this in place? We have this in place. Number one thing is to be able to minimize travel times. The rate at which transportation has grown over the years has moved in a progressional flow. That is, there used to be a time where we don't really have a lot of transportation modes on the road like cars, vehicles, but now in this current age we have a lot of vehicles on the road. So there is a need for us to be able to have this network planning in place in order to be able to reduce the travel time, also to be able to reduce congestion on the road and improve overall accessibility and connectivity between regions, between cities, between locations. So this is going to help us in order to have an economic development. The reason why we feel some countries are economic developed when it comes to transportation, it's because they have been able to maximize their transportation network planning, have it in place, which makes movement and which makes environmental sustainability possible, and also the overall quality of life for residents in the country or in that location or in the city. So throughout a transportation planning process, there needs to be a need for a lot of stakeholders to be able to work together. The ability to collaborate, the ability to work together, the ability to have that unity ensures that any transportation planning process is successful. And who are the stakeholders that we are talking about here? We talk about the government, the transportation agencies and companies. We have other agencies, the community, and the public. Here, when we're talking about the public, we're talking about the users. We're talking about people who make use of the transportation modes or the transportation means in their daily lives. It is very important for them to be able to work together with these other stakeholders to ensure that any transportation planning process is successful. Effective communication and coordination, that there has to be that effective coordination and communication between all parties involved, and that is when any implementation of this plan or initiative can be a success. Now we go into the graph theory. We have been able to look into the introduction of what we call the transportation network. What is a transportation network? And we have also been able to look into the transportation planning, network planning. Now we're going to be looking into what we call the graph theory. Now, graph theory is being said is a branch of mathematics and computer science that studies the relationship between objects. The objects we're talking about here is one we're talking about. It can be in form of the vertices or the nodes, and the connection between the edges. That is the connection between the vertices and the nodes. If we don't want to call it the vertices and the nodes, we can say the nodes and the edges. Because another name for vertex is called the nodes. And for the edges, we can also call them links, we can call them tiles, we can call them relations. But for the sake of this presentation and for the sake of this lecture, we are going to be calling it the nodes and the links, or probably the edges. Just bring it intertwined. Now, this theory has applications in different fields. It's not just in the field of transportation. Even before the introduction in the field of transportation, we have the applications in the field of computer science, in biology, social science, the logistics, and network theory. So it is not just something that it's new. It's not new. So how do we come about the idea of graph theory? How does it come into the picture? So this came into the picture as a result of a specific problem in back then in a city in Russia called Königsberg. So graph theory has a rich history, beginning with a specific problem and evolving into a broad area of study. And this dates back at the time of during the 18th century. Now, the problem in Königsberg was as a result of a bridge problem. So it's called the Königsberg Bridge Problem. The problem was posed in the city of Königsberg, which was divided by a river and connected by 7 bridges. Now this is the idea. The idea is the bridges. Now this is the picture of what we are trying to explain. Now this is the bridge we call it the bridges of Königsberg. We can see the bridges, we can see how they are numbered, number 1, 2, 3, 4, 5, 6, and 7. We can see the connection within the bridge. Now the challenge was to find a way. The challenge is to find a walk through the city that would cross each bridge exactly once. The ability to cross through the bridge exactly once. So you must be able to cross through all the 7 bridges exactly once. And how is that going to be possible? Is it possible? Let us take a look at it. So we have the understanding that this is the bridge. Then here. Now we can have this sample of the bridge. So if you're coming through from this point, you can see from the red sign, you come in from this bridge, you can exit from here. You come in from here into to this bridge, then to this bridge, and to this bridge. You can see that it is very possible. It is possible for us to cross only 6 of the bridges. Then 7 bridge, the bridge 7 was not used. We also have another example, trying it in another dimension, like coming in from the point 1 to point 2, then to this bridge here, moving to bridge 7, then to bridge 3, then we have bridge 5. So at the end of the day, we can see that bridge 2 was not used. So this was a problem. So the ability to be able to cross through the 7 bridges successfully seems impossible. Now, how does the Swiss mathematician came into the picture? That is this man, this man in the picture. We call him Leonhard Euler. Leonhard Euler was able to come into the picture to explain. So he was able to explain that he showed that it was impossible to find such a work, and in doing so, in explaining this, he was able to develop the first principles of what we now call the graph theory. So having an understanding of that is, we say the graph theory plays a crucial role in analyzing and modeling transportation network because we need that connectivity between transportation networks. Transportation networks can be multi-complex. It can be a bit complicated. So the ability to be able to find that connectivity between all different means of transportation networks is where graph theory comes into play. And we say some of these things are represented in form of graphs, where nodes represent the location. I have already explained that, and the edges represent a transportation link here. Now, what are the terminologies? In order to explain this, in which I've already said earlier, we'll come back to this picture again. We have this picture. Now, when we have this generating node and we have this generating node, there is, when we are, if we are to be asked which one has a level of degree of, so we're going to be starting with the terminologies that are used in graph theory. So, well, the first thing that we're going to be looking into will be the graph. Now, what is a graph, which is usually represented with a G? We said it's composed of a set of nodes that are connected by edges, which is the links. So mathematically, it says a graph is represented as G. Mathematically is represented as G, which equals to the vertices and what the edges. So that is what makes up a graph. So the coming together of the nodes and the edges, or the vertices or the links, is what we call the graph. The connection between the two of them is what makes up a graph. And we have different types of graphs in which we'll not be looking into. We have a simple graph, we have a complete graph, we have bipartite graph, weighted graph. Some of it we are going to be looking into still in this lecture, but some of it will not be going into much of it. So they also have what we call the node. The node, as I said earlier, is also called a vertex. Now, we say it's a thing, it's a point, it's a location, maybe in form of a city intersection. So, these are what we call a node in a transportation network. So it can be, so nodes are connected by edges to form the network structure. So node can stand on its own the same way a link cannot stand on its own. So the coming together of the two of them is what makes a network. So we said a node is just what a point of intersection. It might be in form of a bus stop, it might be in form of a railway station, it might be in form of a port, anything. That position, that point, that frame, that location is what we call a node or a vertex. Now we have the edge or the link. So it says it represents the connection between two nodes. So that means it takes two nodes to have a link. So we must have two nodes that connect within one end of a link to the other end, and that is done with a node. So that means what we're trying to say here is the relationship between two nodes, different connection between two or more points or two or more cities, such as the roads, the highways, the railways. These are examples of edges or link in a transportation network. Another name for edge, other than it being called a link, it can also be called tiles. It can also be called relations, but popularly it is called an edge or a link. Now, under this, we also have what we call a directed edge. A directed edge is just something that shows the movement, a connection showing the movement within one edge of the node to another, which has a sign of an arrow that shows that it is directed toward a certain location in a transportation network. So the first three we have here is the graph. Having an understanding of what a graph is, which is the combination of the nodes and the link. Then understanding of what a node is and also what an edge is gives us a good ground on the terminologies that are used in graph theory. So from what I explained earlier, this is just a picture to denote. We can see this is a node, this is a link. Like I said, this can be a location, this can be a point, this can be a city connected to another one here. So this connection between is what we call the link, which can be the road, which can be the highway, which can be a railway, which can be a port, it could be anything. So here we can see what we call a directed flow. We can see the arrow is here, which I explained earlier here, directed edge. So this is just a picture to show us what we call a node. This is a node. Every point of this is called a node. This is also a node, a node. So the line between two nodes is what we call a link. So this is a link, which we also call, if we don't want to call it a link, we call it edges, or we call it relations or tiles. So now that we have a good understanding of what we call a node and what we call a link, there is something we call a unilateral, a unidirectional link, and there is also another one we call a bidirectional link. What do we mean by a unidirectional link? A unidirectional link only connects one node in one direction to another. It's a one-way, like what we popularly call a one-way. So there is no way back. It is just going forward, just that one way, but there is no return. There is no return. But a bidirectional link is a link that shows that there is a movement from one node to another, and the receiving node can also move back as a source node to the first node. From the picture we have here, we can see the arrows that are in blue, just something like this. This node now connects to this particular node. This is a unidirectional link, which shows that there can only be a movement from this node to this node, but there is no arrow movement from this particular node back to this. So this shows that it is uni. Uni means one, which means it is in one direction, just one direction from here to here, but we cannot have a direction back from this node to this. So this, which can be seen with a blue color in this one picture. But a bidirectional link, bidirectional, from the word bi means two. That means it's a two-way, and we can see it is being denoted with this color, that is the black color. Like for example, within this node and this node, we can see there can be a movement from this node to this node, which we have this arrow sign here, and there could also be a movement from this node back to this node, which has this arrow sign. So what we're trying to say is that in a transportation network, there are connections between some nodes and links that can be unidirectional, and there are some connections between some nodes and links in a transportation network that can be bidirectional. So not all connections or networks are one way in sense of unidirectional. Some are unidirectional and some can be bidirectional link. In explaining under this, we have what we call a generating node and we have what we call a demanding node. There is no way we will be talking about this in transportation network that we will not go into what we call a generating node and a demanding node. That means in a transportation network, there can be series of nodes, like what we have in this picture. There are a lot of nodes. All these points where we have this something like 0, 0, 0. These are nodes. All of them are whole nodes. They're whole nodes. Why the line in between those nodes are what we call the links. So, but between all these nodes, there are some of them that we call a generating node. And what is a generating node? If you don't want to call it a generating node, it can also be called a source node. It's a vertex in a graph that produces or generates certain quantity of flow of goods, people, or resources. That means it is from that particular node other nodes can be generated. It supplies, is a supplying node, let me put it that way. It supplies other nodes in a transportation network. So when we have a node that is said to be a generating node, that means it is a source node for other nodes. That is, it is from the nodes all that there is a flow of quantity of maybe goods, it might be people, it might be resources to other nodes. From here, from this point, you can see this particular node here. This node is what we call the generating node. From the nodes we have here, this is the generating node, and from this picture we have two generating nodes. This is a generating node, and there is another generating node here. Then we have what we call a demanding node. But before I go into what we call a demanding node, let me give an example that will lead us to a demanding node with this picture. Now, we can say in a factory, like a factory that produces, let's say, 1,000 units of a particular product. So let's say this generating node here is the factory producing about 1,000 units of a particular product. And when the units of the product are being produced in this node, or in this factory, or in this particular point, there's going to be a point where the products will be sent to other facilities, maybe other stores, or if it's not going to be stores, maybe other warehouses where they will be kept in order for sale or whatever it is. So if we say, as we said, that this is the generating node and here is the factory where all these things are being distributed, which we also call the source node. So there is a need for it to be sent to other nodes where it will be distributed. So that means this is the generating, this is the point where the generation comes into place, where we generate our product, it is being made and it will be sent to every other form of nodes. Now, the nodes that it's the generated from the generating nodes, the other nodes in which it will be sent to is what we now call the demanding node. That is, the demanding node, like I said, it can also be called a sink node. They are vertices that requires or consumes certain quantity of flow. So they are ready to receive. They are ready to receive, just like what we have here. Demanding node. So you can see it has this dot filling around the circle. So that means for this is a demanding node. This is a demanding node. This is a demanding node in this transportation network. Let's assume this is a transportation network. So these are demanding nodes. So the movement from the generating node to any of the demanding node here is what we're trying to say. So a generating node is where it is being produced. A demanding node is where it is being transported to, distributed to, or being received. So for the picture, like we said, we have here, if I have a generating node at this point and I also have a generating node at this point, if I want to supply some of my demanding node, it will be illogical for me to have a generating node here and I'm expecting this generating node to come and supply this demanding node. It is wrong. Why? Because we have a close by generating node here that can easily supply this demanding node, and this generating node can supply this demanding node. This generating node can easily also supply this demanding node, and maybe also supply this demanding node and this demanding node. So where the generating node we have here can supply this demanding node and this demanding node. So this is to tell us that even when, that is why when we have in a particular city, let's use maybe in the United States, you cannot have a facility in New York and you also have another facility, let's say in Chicago, and you're expecting the one in Chicago, the generating node or the facility or a producing warehouse in Chicago to supply the facility in New York. Since we have a facility in New York, the facility in New York should be able to supply other nodes or other facilities within that city. I'm not expecting the one in Chicago to come into supply, just like what we have here. So we cannot have this particular node to come here to supply. Though there might be some exemptions in some cases, maybe as a result of lack of product availability or so, but all things being equal to ceteris paribus, it is expected that the closest generating node should be able to supply the demanding nodes around it. So going further, we also have what we call the weighted edge. And when we say a wedge is weighted, that means when we say something has weight, that means it's measured, it's measurable. That is, it can be in a numerical form. And a hedge, not forgetting when we say what we call hedge, a hedge is also what we call the links that we have here. The hedge is the link. So it can be, instead of we just having it as a line, we can also weigh it up, maybe like the distance from this point to this point. We can say this is 15 kilometers, and the distance from this point to this point could be 12 kilometers. So that means when we add a numerical value to the links, it is now what we call a weighted link or a weighted edge of what we're trying to explain here. So when a numerical value it is attached to it, then it is called a weighted edge or a weighted link. So it can be numerical in form of distance, it can be in form of travel time, it can be in form of capacity, it can be in form of cost. Why is this very important? Why do we have to weigh our edges or our links? In the later part of this lecture, we are going to be looking into that, and I'll be explaining that with some examples. Then we have what we call the degree of a node. The degree of a node. The degree of a node is a fundamental concept in graph theory that measures how connected a node is to other nodes in the graph. And we know we have different forms of graph, the undirected graph, and it is simply the number of edges incident to the node. In a directed graph, it is split into what we call in degree and out degree, depending on the direction of the edges. This particular example we have here, we can see it's not a directed graph, so it can't really help us it can give us a good understanding on this aspect. The degree of a node provides insight into its role in the graph, such as its centrality, connectivity, and the importance in network planning. Still going back to this particular node, we can see this generating node and this particular generating node. These two particular generating nodes we have in this question. This generating node has lots of connectivity to it, from what we can see in the picture, compared to this generating node that has less of it. So this shows the degree of connectivity to this generating node. So that is what degree of a node tells us more about. So moving to the next part, we have the paths, still under the terms in graph theory. A path in a transportation network is said to be a sequence, that is the sequence of connectivity between nodes and edges in a network. So in graph theory, a path is a sequence of edges that connects a sequence of vertices together. So talk about a sequence. One thing that we need to understand about a path is that it comes in form of a sequence. Now, the next point is a circle. A cycle in graph is said to be a path that begins and ends at the same vertex. So it starts and begins. It begins and ends at the same vertex, with no edges or vertices repeated except for the starting and the ending vertex. And we also have a circuit. I'm going to be explaining the breakdown of this in the next slide. Looking at this picture of cycles and circuits. On this graph, when we look at a point 1, 2, and 3, we can see this is a unidirectional link from 1 to 2, unidirectional link from 2 to 4, and unidirectional link from 4 back to 1. So you can see it's a movement. From this is called a circuit. The ability to move in that direction round, you can have it from 1 to 2, 2 to 4, 4 to 1, then back from 1 to 2, and it keeps flowing that way. That is what we call a circuit. But when we have in form of, it says on this graph 2 to 3 and 3 to 6, we also have the 5 and the 2. This movement is called a circle, but it is not a circuit. It is just a cycle, but not a circuit. A circuit involves the movement successfully where it keeps going in a sequential manner, like it can continue the flow. But when it comes to a cycle, the cycle doesn't keep flowing. The flow does not continue. So here it says 1241 is a cycle and a circuit. That is 1241. So a circuit can be a cycle, but not all circuits cannot be a cycle. I'm going to say that again. A circuit can be a cycle, but a cycle cannot be a circuit. So just like what we have here explained from this. So here the movement from 1 to 2 to 4 back to 1, then from 1 again to 4, then back to 1, it keeps flowing. But that flow, when it comes to this, it's not possible. We cannot have 2 to 5, then to 4, then 1, because here is a unilateral. It goes from this point up to 5, but we don't have a flow from 5 back to 4. Let's say we have 2 to 4, then 4 to 5, but we do not have a link flow from 5 back to 2. Assuming we have a link flow from 5 back to 2, then this could have been a circuit and also a cycle. But because we have the movement from 2 to 4, yes, we have the movement from 4 to 5, yes, but we do not have the movement from 5 back to 2, which this shows that it's just a unilateral link. Then this is just a cycle and not a circuit. Then we have what we call the connection. A graph is said to be connected if there is a path in any of the vertices in the graph. When there is a path, then there is a connection. That is just what we're trying to say. When there is a path, there is a graph. And we have what we call the length of a link or the path. So we've been able to measure the length of the link here. It's the total number of edges that can be seen between two vertices. Let's take this for example. If we have a path from A to B, we have paths going from B to C and still going from C to D. If we want to know the number of links, the length of the link of this, that means we have A to B here, and that means from when we get to the B, we have D to C, then we have what, C to D. That means from this, we have 1, 2, 3. The length of the link, in this case, the length is 3 as it consists of 3 edges. We're still going to be looking at more examples on this. Now here we have this, like we said earlier, the connection. This is a connection. 1 to 2 is a connection. As we said earlier, we can also have just this is a connection from this first graph. It says in graph A there are 5 links. From this graph A, yes, there are 5 links. That is 1 to 2. We also have a connection from 2 to 1. So from what we have within, say we have 5 links. That is the link from 1 to 2. Then we have the link from 2 back to 1. So this is what we call a bidirectional link. We've explained that earlier. When it is a movement from 1 to 2 and there is no movement from 2 back to 1, is what we call a unidirectional link. But in this case, we have 1 to 2, then we have 2 to 1. Just we have a 1 to 2, then 2 to 1. Then we also have 2 to 3. That is also a link. We have 3 to 4 is also a link. Sorry, 4 to 3 is also a link. Then we have the movement between this link, that is 4 to 4. That is what it means. That is why we have this arrow sign. It's 4 to 4. And it proceeds to say we have 3 connections. That is, we have connection 1 to 2. Then we have 2 to 3. Then we have the 4 to 3. Now on graph B, there is a path. We said that the path means it keeps flowing. It's a sequence. Just like we have here, 1 to 2, then from 2 to 3. This is a path. So what we have in B is a path. But on graph C, there is no path between. In graph B, we have a path between 1 to 3. That means there is a path leading from point 1 to point 3. But in graph C, there is no movement from point 1 to point C, because here we have a unidirectional link to 2, and here we have a unidirectional link from 3 to 2. but we do not have a link from 1 to 3. So here it says, but on graph 3, the graph C, there is no path between 1 and 3. The length of a link, connections of paths. We already explained what the length of a link is, but we are going to be having a sample breakdown of that with this picture. It says on this graph, the length of link 2 to 3 is 4. Now you can see each of the link has been weighted. That is, the link between 1 and 2 here is 2 kilometers, 2 to 3 is 4 kilometers, 3 to 6, 2 kilometers, then 4 to 7, 4 to 5 is 7 kilometers. This has been weighted. If I want to move from point 1 to point 6, and I have this information, it is very important for me to know the sequence of the movement from point 1 to point 6. So consider which one will give me a lesser kilometer. And that means if it's going to be a lesser kilometer, that means the travel time will also be lesser to move from point 1 to point 6. Let's do this together. If I decide to move from point 1 to point 4, which is 5 kilometers, then from point 4 to point 5, which is 7 kilometers, that makes it 12 kilometers. Then from point 5 to point 6, which is 3 kilometers, like this, because this is the arrow to this place. So that is 5 plus 7 plus 3, that will give us 15 kilometers. That is 5 plus 7, so 12 plus 3, that is 15. But that is not the only path that leads from point 1 to point 6. Let's check if there is any other path that can lead us there. If we decide to move from point 1 to point 4, then point 4 to point 6, point 4 to point 3, there is no path from point 3 to point 6. Why? Because this is a unidirectional link that only moves from 6 to 3, but there is no path from 3 to 6. The same thing for this. From 1 to 2, from 2 to 3, but there is no link from 3 to 6. So that means the only path from 1 to 6 in this picture is this, moving from 1 to node 1 to node 4, then from node 4 to node 5, then from node 5 to node 6, which will be 15 kilometers. Still under the terms in graph theory, we have the shortest path. From the previous example we had, it is only because we had one path that leads us from point 1 to point 6. There are some examples where we have different paths that can lead us from point 1 to point 6. And in that case, we need to look for the shortest possible path that can get us to that point. And that is where the algorithms like Jasper's algorithm comes into play in this topic, like graph theory. We've already explained what a cycle is, and here we are going to be looking at what we call the spanning tree. A tree is a connected graph without a cycle. That is what a spanning tree. We know what a tree is, the roots, the branches. There is no circle. That cycle between them will not come into play in a spanning tree, or when we're dealing with a spanning tree in a transportation network. It just keeps creating a subgraph. So, we have the roots, the root creates branches. Out of the branches creates another form of branches, keeps going like that. So that is what we're saying, a graph creating subgraphs like that. So it says a spanning tree of a transportation network is a subgraph, that includes all nodes. And this is what a tree, this is just a normal tree. It doesn't have anything to do with a spanning tree. I just brought in this picture in order to explain better. Like, this is a tree. We have the roots here that creates this branch. This branch creates another branch. It creates this branch here. It creates a branch. This creates a branch, another branch. It keeps creating different branches. Another branch here, branch. So we have just one tree creating a branch, and that branch also creating other branches. So it's just the same thing we're trying to explain when we're looking into a transportation network. And on the graph, we have a graph creating subgraphs and subgraphs in that manner. Yeah, it's just giving us a vivid example based on graph theory on a tree graph. Now this is the root. The point here is the root. That is our node. This node is the root. So it creates this node, it creates this node, it leads to this node, leads to this node, leads to this node, leads to this node, and leads to this node. So this graph is a tree. Having one node as the roots, this is the origin node producing other form of nodes here. So you can see that it doesn't come in form of a cycle like we had earlier where we can connect them together. But this keeps creating branches and can keep creating. This leads to this, which leads to this, leads to this, and like that. Then we have the root node, just something that I explained earlier. This is the root. This is giving birth to this, and this to this, this to this, and this to this, like that. The root node. Node 1 is the only root of this graph because every other node is part of a path originated from node 1. So when we have a node that is like the originating node, is what we call a root node. The shortest path model is just a concept that helps us to find the minimum distance, or at least the cost path between two vertices in a graph. Is as simple as that. So this model is quite important, and there are a lot of algorithms that are being used to find the shortest path. We have the Dijkstra's algorithm, we have the Bellman-Ford algorithm, we have the Claude-Warshall algorithm. So this is just an overview. There's a whole lot into each of these models. So still on the shortest path model, this is just a sample of a question. If we're moving from a point 1 to a point 6, something similar to what we talked about earlier, but this time around, this is this is a bi-directional link. So this is a bi-directional link, which means it can move from one point to the other. If I decide to move from point 1 to point 2, then point 2 to point 4, then point 4 to point 6. So this is the factory, and this is the warehouse. It shows that based on the demand here is 100, 200, and 100. Which movement will I go through? Since I know fully well that the demands that will give me a higher output from the factory to the warehouse, rather than giving me something shorter than that or lesser than that. From the factory here we have 100 plus 200, that's 300 plus this will give us 400. So if we take this route of from the factory 1 to 2, 2 to 4, then 4 to 6, then we have 400 at this warehouse. If I don't want to go through that route, we have the route 1 to 3, 3 to 5, and 5 to 6, and that is 200, 240, then 340. So 340 is lesser than what we have from 1 to 2, 2 to 4, and 4 to 6, which is about 400. Other than that, we can also have a movement from 1 to 200. Then we have 2 to 5, that's 200. 5 to 4, that's 350. Then 4 to 6, that is 450. So the movement through that path will give us a higher product being moved from the factory to the warehouse at 450, which beats the record of the first one we had from 1 to 2, excuse me, 1 to 2, 2 to 4, and 4 to 6. So this is what it's all about. This calculation now is based on the quantity of goods that are moved. In most cases, it can be calculated. The values or the weighted points can be in form of the distance. And if it is in form of distance, or it is in form of cost, or is in form of travel time, then we are going to look at the shortest, the one that has the least value. Because whichever one gives us the least travel time is the path we'll follow. But anyone who gives us the least distance covered in order to get to move from point 1 to point 6 will be the path we'll follow. Or whichever one gives us the least cost in movement from point 1 to point 6, then that's what we'll follow. The values we have in this particular graph now, if we decide to change it from just being a factory supply to the cost, assuming I am moving from point 1 to point 6, and I'm trying to look at the cost to move from here. So these values are based on cost. Now let's put this in form of maybe dollars. From point 1 to point 2, that's $100. to move from here to here. Then from 2 to 4 is $200. Then from 4 to 6 is $100. So that means from the movement from point 1 to point 6 will cost about $400, which cannot be compared if I decide to take this path of from 1 to 3, from node 1 to node 3, that is $200. Node 3 to node 5, that's $40. Node 5 to node 6, that's $100, which would be $340 compared to spending $400 from the path here leading to this particular point. We can also have other points like node 1 to node 2, $100, node 2 to node 5, $100, then node 5 to node 6, $100, which is $300. And that also beats that of the $340, which makes this lesser. So the idea behind this is the shortest path model is to be able to record that which will give us the least travel time or the least cost or the least distance or the capacity. So it can come in different form. It depends on what you're calculating for. If you're calculating based on distance, if you're calculating based on cost, if you're calculating based on travel time, then you can take that into consideration. So this is an example. If you want to try this on your own using the Dijkstra's algorithm, so it says what is the shortest path to travel from A to Z. So this is A and this is Z. So which one will give us the shortest travel distance? If I decide to move from A to C to E, and this will give us 17. So this will give us, let's say, 17 kilometers. But if I decide to move from A to B, B to D, then D to Z, this is 9 and this is 15. This will give me 15 kilometers. So it takes 15 kilometers compared to moving in this direction or this path that is about 17 kilometers. So there can be other points in which when you check through yourself, maybe it might be lesser than that you can take into consideration before determining or deciding which one is the shortest path to travel from node A to node C. So thank you. So that is it from the transportation network and graph theory. This is just an introduction into it, and I'll see you in the next lecture. Thank you.